Hello and welcome. Let's talk about building a cloud-friendly application today. My name is Larry Garfield. You may know me online as Krell. If you want to make fun of me on Twitter during this talk, that's where you do so. I generally encourage it. I'm a staff engineer for Typo3, the oldest PHP CMS still in the market. I'm also a member of the PHP Fig core committee. The Fig is essentially PHP standards body that publish specifications to help standardize the PHP ecosystem and make it easier for projects to collaborate. I'm also the author of a couple of books on PHP development, including Exploring PHP 8 and Thinking Functionally in PHP. Yes, functional programming in PHP. It's a thing, it's possible, it actually works. But that's not really what we're talking about today. We're here to talk about clouds. Wrong clouds. When I say clouds, we're actually talking about cloud computing. I formerly worked at Platform SH. It's a cloud-based hosting company, which meant, and I worked in developer relations, which meant I got to work with a lot of different applications, trying to get them to run in Platform's environment, which meant I saw a lot of apps that were really, really good, and a lot of applications that, if you can't say anything nice, don't say anything at all, so I won't mention them. But this is important because cloud-based technology is where most of the industry is shifting at this point. Most software has now gone open source. Most cloud-based systems are built on open source technology. More and more software is running in cloud-based environments. If you're building an application today, you have to think about where it's going to be living, where it's going to be hosted, which is almost certainly going to be in some kind of cloud-based environment. Cloud this, cloud that. Okay, what does that actually mean? Well, there's actually two different questions here when we're talking about clouds. One is, what is cloud computing? And the other is, what is the cloud? And these are different things. These are completely separate questions with different answers. The cloud is a marketing term that means someone else's hard drive. This is a business model. It's outsourcing your hard drive to someone else's data center. This has been around since at least the mid-90s. We're not really going to be talking about it, about the cloud that much here. We're talking mainly about cloud computing. Cloud computing is a model of running software that abstracts away physical infrastructure so that you can think of your application as running on a logical computer system that may or may not have any correlation with a physical box sitting under someone's desk or on a server rack or wherever. This is often, probably usually, implemented by a dedicated cloud hosting company, that is the cloud, but it doesn't have to be. You can absolutely do cloud computing on your own hardware in your own data center, or even on your own cluster of Raspberry Pis sitting on your desk. That works. I wouldn't recommend that for production, but you can do it. What this enables, though, is disposable application design. You may have heard the idea in virtualization, the idea that your computer systems should be cattle, not pets, so that you can throw them away and just create a new one when you need to. That's the same idea. This cloud computing is thinking of that same concept of disposable application design and applying it to your application itself, so that when you want to do an update, you don't try and tinker with it in place and change settings. No, you throw it away and install a new copy that is the new updated version. And this gives you a lot of flexibility and a lot of power that we've never had before. But you need to be able to design your application for that, because you can certainly have an application that is not going to play nicely to being thrown out and replaced on a regular basis. So what exactly makes an application cloud friendly? What makes it not necessarily cloud native, but run nicely in this kind of ephemeral cloud-based disposable environment? Based on, again, having worked with a bunch of different systems to try and make them cloud friendly or bend them to be cloud friendly, I've developed a series of guidelines that are good recommendations for designing your application. They may sound familiar to some people if you've read the 12-factor design, but This is guidelines to follow to make your application play nicely in cloud-based environments and with any given cloud-based host. First of all, split your code from your content. This seems obvious, but this is easily the biggest thing people forget and get wrong, especially in older applications. What do we mean by this? Well, first, what is code? Code is data provided by the developer that has been carefully tested, because we're all doing automated testing, right? Its canonical version lives in version control somewhere, because we're all using version control, right? Right? Yeah, okay. And at runtime, it is read-only. You do not want your code changing out from under you in production. That's a security risk. You want your code living on a read-only file system and only changing through a controlled formal process, some kind of deployment process. That is good for security, so that if someone hacks the application, they can't modify the code in place. It's good for auditing. So if something goes wrong, you can audit to check and see, okay, when was this code deployed, who did it, and so on, what change was made. It also means you then can't make a hotfix change in production and then forget to put that in version control and lose that hotfix change the next time you do a normal deploy. Content, by contrast, is provided by users, usually in an ad hoc basis, without any formal testing process. And its canonical version lives either in a database or some kind of writable file system on disk. Key point there being writable. You could be using something like Amazon S3 or another cloud service like that, or it could just be on a local disk on your computer, on your virtual machine. Doesn't matter. The point is, it is writable, which means you can't mix these file systems. Any given directory on disk can either contain code and only code, or content and only content. If you try to put both code and content, both read-only stuff that comes from the developer and stuff that's edited in production, in the same directory, it will break. Because you can't have a directory that is read-only and writable at the same time. That's just not a thing. So make sure that you have your application structured such that those live separately from each other on disk, because you're going to replace one of them separately from the other. Because remember, your application is disposable. Your data is not. If your data is disposable, then you're not actually in production yet, you're just in staging. And even then, you probably don't want to have to manually recreate all of your test data. As you're developing an application, your workflow is going to look something like this. You're doing development on your local laptop or wherever, and you're pushing and pulling to version control as you develop. Periodically, you're going to pull data out of version control and run it through some kind of build process. That build process could be anything. It could be compiling Java code or Go code, downloading additional dependencies, compiling SAS or less files, deleting development pieces you don't want in production. Arbitrary process here that turns what is in Git into a read-only thing you deploy to production. You're then going to take that artifact, that built copy of the application, and install that into a production environment where there is already data waiting for it, that is the actual production data. Periodically, you're then going to take snapshots of that data down to your laptop or a staging environment or so on to make sure that you're developing against real data and aren't going to break anything inadvertently. Note, these are completely different workflows that do not cross anywhere. And there is no in-between option. Fundamentally, keep developer-provided and user-provided files separate from each other. At the directory level, these need to be separate things. If not, then that read-only file system is going to bite you. Next guideline. What about configuration? What is configuration? Well, is it code or is it content? Does it come from the developer or the user? does it fundamentally live in Git, or is it part of your data set? Is it part of the database? Could be either. Depending on what you're talking about, both of these are perfectly viable, valid, correct decisions. But you have to decide. You can't have something that is both code and content. That's not a thing. So you need to decide, is this piece of configuration something that is controlled by a developer and goes through a developer workflow? Or is this something controlled by the user and modified directly in production? For a bespoke custom application, this is usually not much of an issue because configuration is all handled by the developer, not by people pushing buttons in the UI. For an off-the-shelf application, like a CMS or an e-commerce system or a CRM, those very often, their whole selling point is that you can configure it through the UI, through the GUI on the web, which means its configuration is not code, it is data, so you cannot use a code style workflow for it to preview changes, for example. That's not a thing. You have to decide which set of trade-offs you want to have in any given case. By far, the most robust solution to this I've seen is the Drupal CMS. It's one of the large PHP CMSs that I used to work on. In Drupal 8 and version 9, configuration canonically lives in the database, and that it is canonically content in that sense. However, after you're done configuring it in the UI, you can export all of the configuration into YAML files, and you create this gigantic directory full of thousands of YAML files, which you can then commit to Git, push, pull, and so on like any other file. And then when you get into production, you push a button, import everything from disk into the database, overwrite what's in the database, and you've now updated your configuration. This works. It works decently well. It is horribly over-engineered for the vast majority of use cases. And I have not even gotten into a lot of the intricacies around overrides and stuff like that. It took years to build, and it still is only kind of shaky. So don't try that. Don't try this at home. For most applications, just decide if you're dealing with code or content. Do you want the configuration to be controlled by the developer, and therefore it goes through Git, it has branches, you can go through a staging process, or it's controlled by the user, the admin in the UI on the production system, and they can change stuff on the fly. It doesn't matter which one you pick, as long as you pick one and accept whatever set of trade-offs that's going to have, because you have to accept those trade-offs. You cannot have your cake and eat it too. I've never seen a system that truly lets you do that. I don't think it's even possible. We should also keep in mind that what happens at runtime stays at runtime. By that, we mean the data. But you can have multiple runtimes. When we build our application, that application artifact we talked about before, that is built separate from the production environment. And we're then going to slot it into the production environment by popping out the old version and plugging in the new version. And we can do that fairly rapidly. You can deploy all the time this way. But that means the application exists separate from all of the content and all of the services it's connected to. This is also how you're able to then have a staging environment or an integration environment, or even ideally an environment per branch configuration, like the good hosts these days do, like Platform. Maybe you want to have a multi-head configuration or auto-scaling. Then you're going to have your application getting spun up multiple times in production, connecting to maybe the same database, maybe you're in a replica environment. Your application can assume nothing about the environment it's plugging into. Like, what's the IP address of the database? What's the directory on disk where all of the files live? It can't know these things because those are going to vary from one environment to another. So that application cannot have that information hard-coded into it. This also means all of your upgrades are going to involve a restart, because you actually have to remove the old application and plug in the new version. So make sure your application starts quickly. If your application's start time is 3 seconds, No problem. If your application start time is 5 minutes, problem. You now have 5 minutes of downtime every time you want to update your code. That's an architectural problem. Go fix your application. So how do we handle that? Well, dependency injection for your environment, not just for your code. What do we mean by that? Database credentials. That's part of your environment. And database here also includes your search server, your cache server, and so on. Any API keys should not be in your code. They should not be in Git. They should be injected into the environment, because you really don't want to use your production API keys when you're testing your payment gateway in development. Don't ask how I know that. Any paths on disk, the path to your code, the path on disk that your code lives at may vary from one environment to another. Relative paths within your application, that's okay. But the path on disk your application lives on, it's going to be different in different environments, as is the domain name. You have your production domain name, but your staging server is presumably going to be on a different domain name, I hope. And so your application needs to not have the domain name hard-coded into it. This also includes in the database. Domain name in the database or paths on disk in the database are going to cause problems as soon as you move to a new environment, because those values will be different. So how do we inject these? Environment variables. What an ancient tool that still works. Every language has a fairly basic API for accessing system environment variables. Cool, that's fine. Use whatever your language has. But the way that the data gets injected may be different from one host to another. Some hosts may pass in your database information as a single URL string. Some may pass it in as a separate DB user, DB pass, and so on environment variable. Some may pass it in as a series of values, but in a compressed text blob of some kind. So there's really no standard around this. So your application needs to have some way to translate whatever the host has into whatever your application wants, which means you need somewhere to put glue code. And that glue code is going to be a little bit of custom code that is unique to every combination of application and host. There are too many applications and hosts out there to pre-bake everything, so your application needs to have somewhere to put runtime logic to do this kind of translation. At Platform SH, we provided information, these kind of credentials, as a JSON blob that was base64 encoded and then put into an environment variable. So there's a little bit of fairly fast code to pull it out and read it. You can do that manually. We also provided a small utility library. We have one for like 5 different languages. If you're in Java, cool. You import the Platform SH config library, call get credential on it, and pull out the database credentials and format it from MySQL, and you're good to go. If you're in Kotlin, same thing, use the same library because it's all JVM, fine. If you're in Node, same basic idea. You grab the config API object, get out the database credentials, pass them into your MySQL or whatever your database's API is as individual values. Cool, keep on going. If you're in Go, same idea. In Go, you have a package that has a global variable in it that has that lazily created object, and then you can read it. The details are going to vary language to language. We also have a library for Python. We have a library for PHP. Just same basic idea in everything. The idea here is that your application needs to have somewhere to put this code. Doesn't matter, the exact details of it, but there needs to be somewhere to put it. That's fine for production, but what about local development? Well, for local, your best answer then is to use .env files. .env is a loose standard for providing environment variable overrides. There are .env libraries available for every language, usually several. Use whatever you want, pick one, I don't care. The basic idea is you provide a .env file on disk in your application root, and then when your application starts up, it goes to read its environment variables, but first it says, okay, look at the .env file. It's just a bunch of key value pairs. Are there any environment variables defined in that file that are not already defined? If so, use those values from the .env file, which means for local developments, I can just fill in my database credentials and my fake API keys and stuff like that. And my local system will then read that and not bother looking at my environment because I don't want to modify the environment on my actual laptop itself. This also means this is for development only. This is for local only. .env files should never, ever be committed to Git. Ever. Do not put application configuration in these, because that is something that's going to be constant and the same from one environment to another. This is only for environment-specific values that you then are not going to override. You're not going to persist between environments, so you're not going to need to commit them. .env files are only for local development. You do not have them in production. In production, you read from the actual environment variables on the system. Also think about trusted domains. A lot of applications have a feature in them where you have to explicitly allow it to serve certain domains, such as your production domain. This is to avoid cache poisoning attacks, where someone can send a request to a server with a bad host header that says evil.com, and then the application will dutifully use that to generate URLs in the your output, and so then you have a cached page that has a whole bunch of evil.com URLs in it, and great, you've got a cross-site scripting attack. Don't do that. Instead, you explicitly allow the domain, but that's again going to be different, production versus staging versus development, whatever. So that value has to be injected in the environment through an environment variable or some other setting, but that cannot be a hard-coded value. And on most cloud-based hosts, you can't predict what they're going to be because there's a variable number of development environments, a variable number of staging environments. And that's a good thing. It's a great feature, but it means you can't rely on knowing exactly what those are going to be and hard-coding a list. You have to be able to get that information from the environment. It also means if your application is configured using static configuration files like ini or .properties files or some, or a YAML file or some kind of format that you cannot inject runtime values into, that's just not going to work. This is just not going to fly. This is especially a problem for older Java applications. I worked with some that, no names, but they just couldn't run in a cloud-based environment because they had no way to be told what their database credentials were. And that's just not cool. That's a simple change that makes an application completely incompatible with modern hosting. Bottom line here, just dependency inject your environment. What about user configured connections though? A lot of systems let you configure through the UI what your search server is or stuff like that. Especially installers. Installers are a huge problem for cloud-based systems. What does an installer typically do? Well, it starts by asking for database credentials. And then it asks the user for some basic site information, like site title, admin user, stuff like that. Write those database credentials to a config file somewhere. Initialize the database through basic table structure, whatever that's going to be. Write out that basic site info, either to a config file or to into the database, and you're done. Problem. This doesn't work in a cloud-based environment. Everywhere it says write to disk, that doesn't work because the disk is read-only. And things like the database, you ideally, as the developer, never know what the database credentials are. They could potentially change out from under you, and your application gets them re-injected through environment variables. So asking the user for database credentials when they don't know what those database credentials even are is going to be a problem. And please, for my sake, never put that basic site information and the database credentials into the same config file. I have run into systems that put the database credentials and user configuration into the same config file. That is fundamentally incompatible with cloud-based hosting. Never, ever do that. It's just no. If your application does that, you're not allowed to run a cloud-based host. It's just broken. Don't do that. What should you do instead, though? Here's what a better installer would do. First, have a place to pre-include the connection glue. We talked about, that's going to be different for every host and every application. Cool, that's fine. Have a place to pre-include that connection glue. Whatever it is, have it pre-included for the installer. The installer then can check that and say, oh, I already have the database injected via the environment variables. I already have the search index and the cache server injected via environment variables. So I'm not going to bother asking the user for those because I already have them. I know, I skipped that. Cool. And then don't download any code from the installer. Installers should never be downloading additional code. Code only comes through Git, ever. It can download data, like translations, for example, or sample content. That's fine, but no code gets downloaded during the installation process because it has nowhere safe to put it. A number of older systems have in-app, essentially app stores for downloading plugins. That just doesn't work in a cloud environment. That functionality is incompatible with cloud-based hosting. If your application has that, find some way to have it detect that you're in a cloud environment with a read-only file system and just disable that part of the UI. Because again, you can't have your cake and eat it too. You also need to avoid lock-in. We're now talking about the cloud than cloud computing here, but they are related topics. Always make sure that you can take your business elsewhere. This is how you keep your providers honest. Even the hosts you like, even the hosts that you're certain are doing great, you have no problem with them business-wise or ethically, they are not in business for you. They are in business for themselves. Google has killed off, as of earlier this year, 227 total services at least. If your application depended on any of these, guess what? You're now SOL. All of the providers you're working with, your cloud-based host, your third-party services, whoever they are, they have their best interest in mind. You need to have your best interest in mind because they don't. And this is not a slam on those services. I've used many of them. I've worked for some of them. But they are companies and they are in business for themselves, not for you. You need to provide that level of protection for yourself in case their business changes. How do you do that? Quite simply, stick to free software. Use services that you can easily replace, especially not just there's a competitor in the market, but for example, if your database is a Postgres, then if the host you're on goes out of business, you're fine. You can run Postgres yourself. You download the data and spin up your own Postgres database. Not that you're going to, but the fact that you can run your own database means that you can then hire anyone else to do so, and it'll be the same. So there are hundreds of hosts that you can put Go and Postgres on. So if your application is written in Go and PostgreSQL, you have your choice. And if your host goes out of business, changes their pricing model, changes their terms of service, you're fine. You can easily move elsewhere. If your application, however, is physically incapable of running without AWS Lambda, guess what? You are now 100% dependent on Amazon, and Amazon can break you overnight. Not just break your code, break your business overnight if they feel like it. Don't put yourself in that position. How do you avoid it? By sticking with safe services. All of your standard open source tools you're familiar with that you can run yourself on your own hardware, which means you can then hire anyone else to run them on their hardware. What's not safe? Any of these proprietary services that you can't just move elsewhere and have it keep working. Again, I'm not anti-service. I'm not anti using an API service where it makes sense for your application. I'm not against using third-party hosting. I'm anti tying yourself to a third-party company who does not have your best interest at heart. They have their bottom line at heart. This is not a cloud computing problem. This is an outsourcing problem, but you have to be aware of it and have to prepare for it architecturally. And that if that means don't use certain cool sounding services because they lock you into another platform, then it means don't use third-party services that lock you into a platform you cannot escape from. Don't put yourself in those golden handcuffs. And finally, no talk about the cloud would be complete without talking about microservices, because cloud computing is all about enabling microservices, right? And microservices are the future. And microservices are the way you write code these days. And microservices are this and microservices are that. Okay, great. What's a microservice? There is no industry consensus yet regarding the properties of microservices, and an official definition is missing as well. Thanks. That's very helpful. We can talk about the properties of microservices, though, based on Wikipedia and Martin Fowler, who's written a lot of the definitional work around microservices architecture and a lot of other things. A microservice design is built out of single-purpose components. Each of those components then talks to each other over dumb pipes, some generic protocol. Could be HTTP, could be IPC, could be some other tunnel, but it's not an application-specific tunnel. That's why just talking to your database over the MySQL binary protocol doesn't count as a microservice. They are built by separate teams. Each microservice has a separate team responsible for it. And that means that they have independent releases. Your user authentication service can publish a new release and update their code without ever talking to or coordinating with the payment gateway microservice team or the web front-end microservice team. They can all work independently of each other without having to talk. Fundamentally, every microservice treats every other microservice as though it were written by a different company. Basically, they are different companies. They just happen to all be owned by the same parent company, so everyone's paycheck has the same name on it. Otherwise, they are different companies, and you're dealing with them as a separate company. Now, this does have a lot of benefits. Each microservice can be written in a completely different tool. You can build your web front end in PHP, your user authentication system in Java, and your payment gateway in Go. Totally fine, because they're all talking to each other over HTTP and everything speaks HTTP. Means you can have very small, focused, interdisciplinary teams. Every one of these teams has its own developers. Every one of these teams has its own project manager. Every one of these teams has its own architect. Every one of these teams has its own product owner. Every one of these teams has its own designer, if there is a design component to it. Those teams can work independently of each other because they are fully self-contained. This gives you a very strong separation of concerns. So it's not easy to leak functionality in from one system into another when they are completely different teams responsible. It also means that you can scale and evolve these pieces separately. If you want to upgrade your web front end from PHP 7 to PHP 8, you can do that. You don't have to talk to anyone else. If you decide you want to rewrite the payment gateway from Python to Go or from Python to Node, okay, you can do that, and it doesn't affect any of the other microservices. Most of these benefits revolve around it being separate teams. The benefits of microservices are not technical, they are organizational. Remember Conway's law. Any organization that designs a system will produce a design whose structure is a copy of the organization's communication structure. The whole point of microservices is not you want these pieces separate, so you're going to give them separate teams. It's you build separate teams and thus you will get separate pieces. You are structuring your HR. This is HR-driven development. You're structuring your teams team structure, your human resources, your developer teams into separate pieces so that they result in separate components that are decoupled from each other, which sometimes you want, sometimes is beneficial, but there are drawbacks to it. For instance, network latency. Calling from one function to another within an application is measured in nanoseconds. Calling from one application to another over the network is measured in microseconds. We're talking orders of magnitude slower execution here. Even if it's on the same data center, they may or may not be on the same physical box depending on the cloud setup. It also means you now have numerous additional points of failure, and points is plural, because once you introduce network logic to something, there are 15,000 new places that something can go wrong and will go wrong. It means your failure rate for calling from a function to a function may be 1 in a trillion. Your error rate from calling from a microservice to a microservice is maybe 1 in 1,000, which is going to happen several times a day. So your application needs to be able to handle, just sometimes the user authentication service doesn't respond because gremlins, and you don't know why, but you have to handle it, which means a lot more error handling, a lot more robustness around where these pieces talk to each other, because so many more things will go wrong. It also means refactoring the overall system becomes vastly harder. If you're refactoring a monolith system, a single application, cool, you just commit new code, move stuff around, your IDE will do half the work for you. If you want to move some functionality from the user authentication microservice to the payment gateway, you're rewriting it from scratch, because it's not just a different team, it could also be a different language, probably is a different language. So you're starting over. You can't reuse anything. You also have to deal with API versioning. If anyone who's done REST work, to build a REST API knows there are 3 different ways to do API versioning in REST. All of them are wrong. There is no correct way. There's just which broken way is going to actually work for you. And guess what? You now have to deal with that whenever any of your microservices are talking to each other, because if you're changing the API on your user authentication system, guess what? The code in the payment gateway or the code in the the web front end, they haven't changed yet. They don't know about the new API. So you have to support the old API for as long as they are still running until they get updated, which could be, I don't know, it's a different team. You have no control over them. Could be years. You also need more staff, because every one of these teams has their own project manager, has its own developer, has its own designer. You are not sharing code, you're not sharing people between these teams. So you probably need more people overall just to handle each of these teams individually. Depending on your system, there may be additional overhead for every request, because not just the network latency time, but the application needs to take time to start up, receive a request, parse it, figure out the routing for it, and so on. It's especially a problem in something like PHP or Python that don't have a persistent process. Every request starts a new, not necessarily spawns a new process, but restarts the application. So there's extra overhead in there for every request that is then going to impact every single user request. That adds up fast. Fundamentally, if one of your microservices is going down, means the others don't work, then guess what? You don't have a microservice, you have a distributed monolith. And that means you have all of the problems of monoliths and all of the problems of microservices and none of the benefits of either. So what should you do instead? I would argue the vast majority of cases do not need microservices. Unless you are Google, Netflix, or Amazon, you don't need microservices. What you need is a multimodal monolith. This is a term I've coined. What is a multimodal monolith? It is usually built by a single team out of good discrete components, because that's just good design in general. And the whole thing deploys at once. Anytime you update, you're updating every component at the same time. So you have no API versioning to deal with. Usually it will all be built in one language. Not always. Sometimes you can use 2 but most of the time you can just use a single language for everything. And it's okay for them to share data stores. Typically in a microservice and setup, every backend has its own database and you never talk to a different service's database. In this case, it's totally fine. They all share the same database. Also, you probably have done this at some point already. What are some examples? Cron jobs. You have some code that's going to take a while to run, say firing off some emails. So instead of doing that in the user request, you toss it off to a cron job and the cron job does it later. That's a multimodal monolith because you have a separate component working on the same code base and the same data, just in a separate process. Queue workers, same idea. You throw data into a queue, the request keeps on going, and then the queue workers do their thing separately. A lot of applications will have a separate admin application, 90% the same code, probably entirely the same code, just a flag that's set to say, hey, turn on the admin here and not turn it on here, which then means you can scale them independently. If you have one server that has your admin application and 3, 4, 5, scaling user applications, all using the same code, then you can scale up your user front end as needed without impacting the admin. And if you get hit with heavy traffic or DDoS or something on your user front end, your admin doesn't care. It's a separate application. A lot of systems have a separate API application to handle non-HTML responses because they were built as an HTML application initially and then tacked on an API. That's fine. All of these could live in separate container instances using the exact same application code in the first place, just with different runtime settings. What do they all have in common? All of these are happening on an asynchronous boundary. Every given user request only touches a single one of these different parts of the system. A given user request may trigger 50 queue items to get set, but that's fine. The actual work happens in a separate request. An admin process is a separate process from a user request. So these things are not going to bump into each other. Again, different languages are well suited here. Ironically, PHP is beautiful for this model. PHP handles this model fantastically. I've seen some older Java applications that were built on this model as well, but very, very heavy. This is still more complex than a monolith. There are still more moving parts here, but it's still vastly less than your microservices setup because everything is in a single code repository. There's only one repository to work with here. There's a single team working on it. And even if you're spinning up multiple containers out of it, that's just multiple build artifacts. It's a single input, and that makes it a lot easier to manage. In summary, then, to make something cloud-friendly, don't assume things. Don't assume the environment your application is going to run in. It will change. Don't assume the number of webheads that your application is going to have when it's running. That will change. Don't assume what the connection information is for your application to talk to third-party gateways or your database or your cache server. Those will change. Don't assume the domain name your application is running on. It will change. Don't assume you can write to disk. You can't if you're doing it right, except in very select areas that are just for user data. But your code should not be writable. That's a separate pathway. Don't assume third-party services that you're using are going to exist forever. They won't. Don't assume that your use case is big and complex enough that you actually need microservices. You probably don't. And by not assuming these things, you make your system more flexible and able to run in a variety of different environments. And that is how you make it cloud-friendly. Thank you very much. Hope you enjoy the rest of the conference. Take care.